Hi everyone! Welcome to our lesson in Finite Mathematics 1. Today, we will learn how figures are reflected, how to identify the line of reflection, and how reflection appears in real-life situations. This lesson is part of Week 1, Day 3 of our Finite Mathematics 1 class. Previously, we started discussing geometric transformations. Today, we will focus on one specific transformation, which is reflection. This is important because reflections are commonly seen in patterns, designs, artworks, architecture, and even in nature. By the end of this video, you should be able to do three things. First, you should be able to define geometric reflection and identify the line of reflection in a figure. Second, you should be able to perform and illustrate reflections of points and figures on the coordinate plane using the correct reflection rules. Third, you should be able to appreciate the importance of reflections and symmetry in real-life situations and patterns found in the environment. So habang nakikinig kayo, always ask yourself, ano ang nagbabago kapag nire-reflect ang figure? Ano ang nananatili? At saan makikita ang reflection sa totoong buhay? Let's begin with the basic idea. One type of transformation uses a line that acts like a mirror. The image of the figure is reflected across that line, and this transformation is called a reflection. The mirror line is called the line of reflection. So in simple terms, a reflection is a flip. The figure is flipped over a line just like how an object appears in a mirror. The original figure is called the pre-image, while the figure after the reflection is called the image. A reflection in a line is a transformation that maps every point in the plane to another point. Let us look at the first property. If a point is not on the line of reflection, then the line of reflection becomes the perpendicular bisector of the segment connecting the point and its image. Medyo mahaba pakinggan, so let us break it down. Perpendicular means the line forms a 90-degree angle. Bisector means it cuts something into two equal parts. So kapag ang point A ay nireflect at naging A prime, the line of reflection cuts the segment between A and A prime exactly in the middle, and it forms a right angle. That is why the original point and the reflected point are always equally distant from the line of reflection. Now let us look at this triangle. We have triangle ABC on one side of the line of reflection. After reflection, we get triangle A prime, B prime, C prime on the other side. Point A corresponds to A prime. Point B corresponds to B prime, and point C corresponds to C prime. Notice that the triangle did not become bigger or smaller. Same size pa rin siya, same shape pa rin siya. The only thing that changed is its position and orientation. It was flipped over the line of reflection. This is why reflection is considered a rigid transformation because the figure keeps its size and shape. Now let us look at the second property. If a point is on the line of reflection, then the point does not move. In symbols, the point and its image are the same. For example, if point P lies exactly on the line of reflection, then after reflection, P prime is still in the same location. This makes sense because kapag ang point ay nasa mismong mirror line, wala na siyang distance from the mirror. So wala siyang lilipatan sa kabilang side. So remember, if the point is away from the line, it moves to the opposite side. If the point is on the line, it stays in place. Let us try our first example. Here we are asked to graph the given reflection. First, point H is reflected in the x-axis. Second, point G is reflected in the line y equals 4. For this example, we will use the idea that the line of reflection acts like a mirror. The reflected point must be the same distance from the line, but on the opposite side. For part A, point H is reflected in the x-axis. The x-axis is our line of reflection. From the graph, H is 2 units above the x-axis. Therefore, H prime should be 2 units below the x-axis. So we count the distance of H from the x-axis, then copy that same distance on the other side. This is the key rule. Equal distance, opposite side. So if h is above the x-axis, h prime will be below the x-axis. For part B, point G is reflected in the line y equals 4. First, we graph the line y equals 4. This is a horizontal line. Then we plot point G. From the graph, we can see that point G is already on the line y equals 4. Since point G lies exactly on the line of reflection, it will not move. Therefore, G is equal to G prime. This follows the second property of reflection. Points on the line of reflection remain fixed. Now we move to reflections on the coordinate plane. When we reflect points in the coordinate plane, we usually follow coordinate rules. For example, when reflecting a point over the x-axis, the x-coordinate stays the same, but the y-coordinate changes sign. So the rule is, a point x comma y becomes x comma negative y. For example, if the point is 3 comma 4, its reflection over the x-axis is 3 comma negative 4. When reflecting over the y-axis, the y-coordinate stays the same, but the x-coordinate changes sign. So the rule is, a point x comma y becomes negative x comma y. So for example, if the point is 3 comma 4, its reflection over the y-axis is negative 3 comma 4. Now, the rule depends on the line of reflection. So always identify the mirror line first. If the reflection is through the origin, then the rule states that you have to change the sign of both your x-coordinate and y-coordinate. This means that if you have 3 comma 2, then it becomes a negative 3 comma negative 2. And if your reflection is through the line y equal to x, the rule is you interchange your x and y coordinate. So if you have x comma y, the reflection is going to be y comma x. So if your point is 1 comma 3, the reflection of that point is going to be 3 comma 1. Reflections and isometry. Reflection is an example of an isometry. An isometry is a transformation that preserves the size and shape of a figure. This means that when a figure is reflected, the image is congruent to the pre-image. So if the original figure is a triangle, the reflected image is still the same triangle in terms of size and shape. Reflection preserves distance, angle measure, betweenness of points, and collinearity. In simpler terms, hindi nag-iiba ang sukat, hindi nag-iiba ang angles, and hindi nasisira ang structure ng figure. The figure is only flipped. Now let us connect reflection to symmetry. Some figures can be folded so that the two halves match exactly. The fold line is called the line of symmetry. A line of symmetry is also the line of reflection because one half of the figure is the reflection of the other half. For example, think of a heart shape, a butterfly, or some letters of the alphabet. If you fold them along the correct line, both halves will match. So symmetry is actually an application of reflection. Aside from a line of symmetry, some figures may also have a point of symmetry. A point of symmetry is a common point of reflection for all points on a figure. This means that the figure has a center point where the parts of the figure corresponds to each other. In many designs and patterns, point symmetry helps create balance. This is why symmetry is often used in art, logos, architecture, tiles, and decorations. So again, reflection is not just a drawing skill. It helps us understand balance and structure in visual designs. Now let us answer this example. Triangles can have different number of lines of symmetry depending on their shape. First, an equilateral triangle has 3 equal sides and 3 equal angles. Because of this, it has 3 lines of symmetry. Second, an isosceles triangle has 2 equal sides. It has 1 line of symmetry, usually from the top vertex down to the midpoint of the base. Third, a scalene triangle has no equal sides. Since all sides and angles are different, it has zero lines of symmetry. Now let us look at a real-world example involving miniature golf. Adele and Natalie are playing miniature golf. Adele says that reflections can help make hole-in-one on most miniature golf holes. The question is, how should Adele putt the ball to make a hole-in-one? At first, we might think that she should aim directly at the hole, but in this situation, the border may block the direct part. So instead of aiming directly, we can use reflection to find the correct path. If Adele tries to putt the ball directly to the hole, the ball will hit the border and may not go toward the hole. So what can she do? She can mentally reflect the hole across the line that connects the right border. This reflected hole acts like an imaginary target. If she aims the ball towards the reflected image of the hole, the ball will strike the border and rebound towards the actual hole. This works because the path of the ball follows a reflection-like behavior. The angle going toward the border is equal to the angle going away from the border. So reflection helps us predict the correct direction of the shot. Now let us look at another application of reflection. Two houses are located near a rural road. We want to place a telephone pole on the road at point C. The goal is to choose the location of C so that the total length of the telephone cable is minimum. In other words, we want to find the shortest possible total cable length from one house to the pole and from the pole to the other house. Instead of guessing, we can use reflection to solve this. To solve this, we reflect one of the houses across the road. In this case, reflect point A across line M to obtain point A prime. Then, draw a segment from point B to point A prime. The point where the segment intersects the road is labeled as point C. That point C is the best location for the telephone pole. Why? Because a straight line is the shortest distance between two points. Now let us explain why point C gives the minimum cable length. Since A prime is a reflection of A across line M, the distance from C to A is the same as the distance from C to A prime. So instead of thinking of the cable length as AC plus BC, we can think of it as A prime C plus CB. And the shortest path from A prime to B is a straight line. Therefore, placing the telephone pole at point C gives the minimum total length of cable. This is a very useful application of reflection in solving shortest distance problems. Now that we understand what reflection means, let us look at different ways to represent it. There are three methods. Method 1 is the coordinate mapping method. Method 2 is the symbol or notation method. And method 3 is the verbal description method. These methods all describe reflection, but in different forms. Some use coordinates, some use symbols, and some use words. So the first method is the coordinate mapping method. This method uses coordinate rules to determine the new position of a point after reflection. For example, if a point is reflected over the x-axis, we use the rule x, y becomes x, negative y. If a point is reflected over the y-axis, we use the rule x, y becomes negative x, y. In the figure, notice that the distance from the original figure to the line of reflection is the same as the distance from the reflected figure to the line of reflection. So when using this method, we focus on the coordinates and apply the correct reflection rules. The second method is the symbol or notation method. This method uses symbols to describe the reflection. The letter R stands for reflection. The subscript tells us the line of reflection. And the figure inside the notation is the pre-image or the original figure. Then the result is the reflected image. For example, if we see notation involving R, we should ask, what figure is being reflected? Over what line is it being reflected? And what is the resulting image? This method is shorter and more formal, so it is commonly used in textbooks and written mathematical solutions. The third method is the verbal description method. This method uses words to describe the movement of the figure. For example, reflect the figure over the line of reflection or reflect the figure over the x-axis. This method is easier to understand because it directly tells us what to do. But when solving, we still need to know the correct action. If the instruction says reflect over the x-axis, the figure flips above or below the x-axis. If the instruction says reflect over the y-axis, the figure flips left or right across the y-axis. So even if the instruction is written in words, we still apply the reflection rule. That ends our discussion on geometric reflections.